All right, what is up, everybody? This is Brenton again, and I'm doing my part 2 video. This one's going to be focused on just a single action potential and how it is generated. So, let's start with where we left off last time, all right? So, we had a cell, right? We determined that there is a resting membrane potential of about negative 65 millivolts, which is mainly contributed by potassium and sodium. So high K plus inside, low outside, and then low sodium inside, high sodium outside. So there was calcium and chlorine as well, but we don't need to worry about those as much for this discussion. We've come to the conclusion negative 65 millivolts. So this is really important because the reason why we have negative 65 millivolts in the first place was because of permeability of potassium, because they have those potassium leak channels, if you remember. Well, action potentials take advantage of permeability, again, to be able to generate a signal that can be sent down an axon of a neuron. So what happens is, so let's draw a little graph here. This is the most important figure probably to explain. So pretend that we have like a membrane potential here, and we have just time. A whole action potential takes about 2 milliseconds. Just so you're aware, it's not super important, but so pretend we're sitting right here, right? We're at negative 65, and this is measured in millivolts, right? So we're sitting at negative 65. Once you get to a spot between negative 65 and 40, we'll say like negative 50, because that's probably about when it's really significant. So pretend that you depolarize this membrane. This can happen a few different ways, but one is definitely by a previous action potential, which can depolarize it enough. It reaches the spot for another channel, so it reaches the threshold for a channel, which is a voltage-gated sodium channel. So let's just draw that like just a box again. Mm-hmm. All right, we have these little cute red channels that open once the membrane is depolarized enough. Once they open, this is specific to sodium, and based on concentration gradient and, in this case, electrical potential, sodium, let's do that in white, sodium rushes inside the cell. All right? Then, so once this sodium starts pouring into the cell, you get a depolarization rapidly of the membrane. All right, so let's show that. So we get high and fast depolarization of the membrane. Okay, and it even overshoots is what they call it. So here's like 0. It even goes to about 40 millivolts, right? Once this happens, once it gets depolarized enough, these sodium channels close, and voltage-gated potassium channels open. So what if you had some voltage-gated potassium channels? These aren't just your typical little leak channels. These allow for high amount of ion flow, and these ions start flowing out of the membrane quickly. So we get a rapid, what we call hyperpolarization. So fast, it's going, and it gets to negative 65 millivolts, and even what we call undershoots it until these voltage-gated potassium channels close. So it gets about, we'll say, around negative 80 millivolts, where like potassium's equilibrium potential is. So undershoots your resting membrane potential, and gets even closer. So as this happens, so this stops once voltage gated potassium channels, basically they clog up and they inactivate. And then it's necessary to have a repolarization of the membrane back to -65. Sorry, it's a little choppy, and that's -65. All right, pretend that's 65. So, like I said, we have multiple phases here. We have depolarization enough to reach threshold for voltage gated sodium channels. Depolarization, inactivation of voltage gated sodium channels. You reach threshold along the way for activation of voltage gated potassium channels, which then create a huge outpouring of potassium from the cell till you overshoot. So this is the undershoot. This is the overshoot. Till you undershoot, and then you repolarize back to resting membrane potential. Now, just two more things. So you can't regenerate an action potential within this period. All right, you have, well, especially within this period. So you have something called the absolute. Let's say it's right here. This is our. So from this area right here is our absolute refractory period. Absolute refractory. And what basically is happening here is that you have to the cell has to wait for the membrane to become sufficiently negative in order for sodium channels to activate again. So they're up here, they inactivate. For them to be able to activate again, you have to be low enough in membrane potential. And then here, from here to whenever it reaches, it repolarizes back to the -65 millivolts. This space is called your relative refractory. Let's see. Refractory period. All right. And this is when, this is because the membrane stays hyperpolarized until the voltage-gated potassium channels close. And so those will not be able to work until they become unclogged again, which isn't until you repolarize enough to the resting membrane potential. So this is how one action potential is generated. And once again, I hope you guys learned a lot.